In this presentation, we will discuss the distinction between explanatory and response variables and how to use regression analysis to explore the relationship between them. We will also learn how to calculate and interpret residuals, and we'll discuss the assumptions that correlation and regression rely on. When investigating relationships, correlations only show the degree to which variables associate with one another. However, most of the times, a simple association does not provide sufficient information or enough evidence to answer our research question. Regression analysis, however, allows us to predict or to explain the variation in one variable based on another variable. The variable that we are trying to explain, to predict, is called the response variable or the dependent variable because it depends on another variable. The explanatory variable is the variable that we use to explain or to predict the response variable. We also call the explanatory variable the independent variable because it is not a function of another variable. While with correlation the order of the variables doesn't matter, in regression the order of the variables is very important. Also, when we represent these variables graphically, if we only use correlations, it doesn't matter which variable goes on the x-axis and which goes on the y-axis. But when we're conducting regression analysis, we always represent the independent variable or the explanatory variable on the x-axis and the dependent variable or the response variable on the y-axis. For instance, let's say that we already know that there is a significant correlation between the students' GPA and their self-esteem. Our next question could be, can we predict students' scores on a self-esteem scale based on GPA? In other words, does GPA explain self-esteem? These are the types of questions that regression responds to. Note that these questions do not imply a causal relationship. To continue with our example, if we want to predict self-esteem based on GPA, we must first create a plot and to put GPA on the x-axis because this is our predictor, our independent variable, and self-esteem on the y-axis because this is our dependent variable or our response variable. We already know that a scatter plot of two variables that are strongly related tends to describe a line, but we don't have to use our imagination or to guess where the line would be located because there are computation procedures that we could use to obtain this information in a much more precise way. This is what regression analysis does. It identifies a line, which we call the regression line. And this line shows how much and in what direction the response variable changes when the explanatory variable changes. Most individuals in the sample are not located exactly on the line. The line is just a summary of the relationship between the two variables for the entire sample. You may now say, okay, it is nice to have a line to see the direction of the relationship, but is this line really necessary or how is it useful? Well, the regression line has a very important role because it helps us make predictions. For instance, if we already know that GPA is related to self-esteem, when we don't have any information about a student's self-esteem because we didn't measure it, we can predict the student's score on the self-esteem scale based on his or her GPA. For instance, based on the information in this sample, we can predict that a student with a GPA of 2.0 will have a self-esteem score of 78 or 79 on this self-esteem scale. We can estimate the score simply by looking at the graph. If we draw a straight line from the point that represents the 2.0 GPA to the regression line, we find the point on the regression line where this student would be located. Then if we draw a line from this point to the self-esteem axis, we find a self-esteem score that corresponds to the 2.0 GPA. Of course, statisticians would never rely simply on eyeballing and drawing lines to predict scores. So there is a much more precise way, a mathematical way to predict scores on one variable based on another variable. The response variable can be predicted based on a very simple equation. The notation for the predicted value is a lowercase y with a hat, and we call it y hat. In our example, y hat represents the student's predicted self-esteem score. To obtain the predicted value, we need three pieces of information. One of them is the value of the explanatory variable, which in our example was the student's GPA, and we use a lowercase x to represent this variable. We also need two other pieces of information that are typically provided by statistical software. One of them is called the intercept, which is a constant and represents the value of the response variable when the explanatory variable is equal to 0. This is a starting point, if you will, a value that is added in every equation. That is why it's called a constant. The notation used for the intercept is a lowercase a. The other piece of information that we need is also provided by software and is a coefficient that shows how inclined the regression line is. That is why it's called the slope. And we use a lowercase b for value. So to predict a score, all we need to do is to multiply the explanatory variable by the slope and then add the result to the intercept. We can see in our example that our response variable, self-esteem, can be predicted based on GPA using the regression formula. The intercept in our case is 71. This is the value of self-esteem when GPA is equal to 0, so it's our baseline, if you will. The only other piece of information that we need is the slope, which shows the inclination of the regression line, how steep or how flat the line is. In our case, the slope is equal to 4. To obtain the self-esteem score, all we have to do is to multiply the student's GPA, which is 2, by the slope, which is 4, and we get 8. Then we add 8 to the intercept, which is 71, and we get the self-esteem score, which is 79. And this is all we have to do, very simple. So if we know the slope and the intercept, we can predict self-esteem scores based on any GPA. To make sure that you understand the procedure, try to estimate self-esteem scores for other GPA values, and then see if the values you obtain by applying the formula match what the graph is showing. For instance, what is the predicted self-esteem score for a GPA of 1.0? The regression line is obtained by applying what is called the least squares computation procedure. As you noticed in the graph presented earlier, individual points are located around the line. Very few points, if any, are exactly on the line. To obtain the best approximation possible of the data, the line is placed in the location where the distance from all the points to the line is minimal. You also notice that some of the points were above the line while others were below the line. If we compute differences from these points to the points on the line, some differences would be positive while others would be negative. Because the direction is not important here, these differences were squared. That's why the method is called the least squares, because the square distances were used for computation rather than simple differences. As it was mentioned before, the slope and the intercept of the regression line are computed by statistical software for us, but it is important to know how they are computed to understand their meaning. The slope of the line is a function of the correlation between the two variables multiplied by the ratio of their standard deviations. Sy is the standard deviation of the y variable or the response variable, while Sx is the standard deviation explanatory variable. The intercept is the difference between the mean of the response variable and the product of the slope and the mean of the explanatory variable. As you noticed before, the slope of the regression line depends, among other factors, on the correlation between the two variables. The stronger the correlation between the two variables, the higher the slope. The correlation coefficient also helps us identify the percentage in the response variable that is explained or can be attributed to the explanatory variable. In other words, how good is the explanatory variable at predicting the response variable. And this percentage can be obtained simply by squaring the correlation coefficient. The result represents the coefficient of determination, and we use the notation R squared for it. In our example, the correlation coefficient was 0.3, a fairly small correlation. If we square this number, we obtain 0.09, which means that only 9% of the variation in students' self-esteem scores can be explained by their GPA. This coefficient is a statistical measure of how well a regression line approximates real data points. We can now have a better understanding of why only correlations that are above 0.7 are considered strong correlations, because if we square the value 0.7, we obtain 0.49. So we can explain approximately half of the variance in the response variable. So only correlations that are 0.7 or stronger can explain at least half of the variance. The rest of the variance remains unexplained and is attributed to other factors that were not included in the regression equation. It is important to remember a few facts about the least squares regression. The first one is that the order of the variables is very important here, and that we have to make a clear distinction between the explanatory variable, which is represented on the x-axis, and the response variable, which is represented on the y-axis. The terms explanatory variable and response variable are very helpful because they're very explicit, but researchers mostly use the terms independent variable and dependent variable, respectively. Remember that when correlations are positive, the line that represents the relationship goes up. Therefore, the coefficient that represents the slope is also positive. When the relationship is negative, the line goes down, so the slope coefficient is negative. As you have seen in our example, not all the points on the scatter plot are located on the regression line. In fact, only a few points are located very close to the line. However, the mean of the two variables will always be located on the regression line. Other facts that we must remember about regression are that R squared is called the coefficient of determination, and it represents the proportion of variance in the response variable that can be attributed to the explanatory variable. As you have seen on the previous slides, regression coefficients are used to predict the response variable based on the explanatory variable. For our example, the regression equation is self-esteem equals 71 plus 4 times the student's GPA. And we can use this equation to predict self-esteem scores based on any GPA values. For instance, if a student's GPA is 4.0, based on our equation, the self-esteem score would be 87. However, if we look at our graph, we can see that there is a student who has a GPA of 4.0, but his self-esteem score is higher than 87. It is actually 95. If we subtract the predicted score from the observed score, we obtain a difference of 8 points. This difference is called a residual. When the relationship between the two variables is strong, the residuals are small because the data points are clustered around the regression line. For the points that are located above the line, residuals are positive. For the data points located below the line, residuals are negative. And the mean of all residuals is always equal to 0. Because regression coefficients are computed based on the mean, standard deviations, and correlation of the two variables, they are sensitive to outliers. Therefore, the location of the regression line can change significantly when there are outliers or extreme cases in the dataset, especially if these extreme values are recorded for the explanatory variable. In our example, we have an outlier who has an extremely low GPA and a very high self-esteem score. We can see in the graph on the right that when this outlier is removed, the slope of the regression line is higher, and the line fits the data much better. Most of the data points are close to the line, and therefore the residuals are much smaller. When using regression analysis and interpreting the results, it is very important to keep in mind a few facts. First of all, the relationship between the two variables must be linear, and we have to check this assumption. Another thing that we must remember is that results are affected by outliers. So, when interpreting the results, we should not look only at the regression coefficients that the statistical software computes for us. We should also plot the data to see if we have any outliers and if we can justify removing the outliers from the analysis. Another important thing is to make sure that we do not generalize the results outside of the range of the explanatory variable. For instance, if we try to use age to predict the capacity of working memory, and we only use college students in our study, we should not generalize our results to all ages. We must also think about a possibility that the relationship between two variables is not a direct one. It might be mediated by a third variable, which is not included in the study, but has an effect on the relationship between the variables that are included in the regression equation. Other terms that are used by statisticians for this third variable are confounding variable or hidden variable. When a confounding variable is present, statisticians say that the relationship between the two measured variables is spurious. In educational research, for instance, poverty is often used to explain students' achievement, when in fact it is not poverty per se that impedes students from learning. Other factors that are related to poverty, such as parents' education level, may be a confounding variable. Some studies show that when parents' educational level is higher, children perform better in school, even if the family has a low income. And last but not least, we should always be careful when we report our results when using regression analysis. Even when we predict the values of the response variable or when we explain its variance, we cannot infer that there is a causal relationship between the explanatory variable and the response variable.